So our second application for rates of change is going to be velocity and acceleration and also speed. So we've actually talked about this quite a bit in our videos. These are very important concepts, especially in physics. So let's start off with the definition. We're going to formalize it now. Velocity, or the instantaneous velocity, is the derivative of the position function with respect to time. So you can see that here. Velocity equals ds dt. Remember, s is your position function. And this is the formal definition. Now, you can use your derivative rules, as long as they give you a function, to find the velocity. You don't have to use the limit definition anymore. Remember, we've talked about this briefly. Speed is the same as velocity, but with an absolute value sign, so it's always positive. It doesn't have a direction with it. It just tells you the speed. Whereas velocity is speed and direction. So let's see if we can talk about a graph and how this graph can inform us more about what's going on. All right, so in this case here, we have velocity graphed compared to seconds. So when your velocity is going up, your velocity curve is increasing. What does that mean your car is doing? This is talking about the speed of your car. The speed of your car is increasing, so you're speeding up. That's positive and up and above the x-axis, therefore you're moving in the positive direction. Traditionally, positive direction would be to the right or up. Then we level out here at the top. So at the top we have this flat part here. When you flatten out your velocity, it's not that you're slowing down, it's not that you're stopping, it's that you're leveling out your speed. So think of it as your cruise control being locked in. So you have steady speed, whatever that speed may be, and then you start to slow down until you get to this point here. This point here, your velocity has achieved 0. But you don't stay there for very long. You hit 0, and then what do? You go into a negative velocity. Velocity is below the x-axis, so all of these have negative values. What does that mean if your velocity is negative? That means you're now heading in the opposite direction. So traditionally, opposite would be left or down. So you're heading the opposite direction and you're getting faster and faster and faster because your speeds are increasing in the negative direction until you hit this point. This is the fastest you go in the backwards direction. And then you slow it down because your speed starts to go back towards 0. You're still going in the negative direction because all of these are negative speeds, but you're slowing down until you come to a stop. Now notice this time we stay at 0 for a while. So that means you are stopped for 1 second, apparently, from 5 to 6. But then you start to speed up and you start to go in the forward direction again, or the up direction. You're speeding faster and faster and faster, and then our story ends. Okay? So that's what we can learn by looking at the graph of the derivative. We can analyze what's happening in terms of the motion of the object. So once we have velocity, then we can move on to the next topic, which would be acceleration. So acceleration we denote by a of t. Acceleration is the derivative of the velocity with respect to time. So it's the change in velocity over the change in time, which means it's how much your velocity is changing. So are you accelerating, or are you decelerating, or are you staying constant in your acceleration? Whereas over here we have the second derivative of position with respect to time 2 times. So these are the relationship between the three. We start with position, then we talk about velocity as being the first derivative of the position, and then we can talk about acceleration being the derivative of velocity, or the second derivative of your position function. All right, so we're going to use all of those to solve some problems. Let me bring those up. All right, so here we have an example. A dynamite blast, so it sounds exciting, blows a heavy rock straight up with a launch velocity of 160 feet per second. That's about 109 miles per hour. I do not want to be anywhere near this rock or the dynamite. It reaches a height of s, so s is our position function, remember. Position. So as time goes on, if you look at the picture here, first our rock goes straight up, but eventually gravity takes over, the rock comes to a stop and goes back down. Question, how high does the rock go? How high? Well, we want the highest point it achieves. So this rock leaves the ground and it's shooting up. But as it shoots up, what does it do? It slows down. The highest point it reaches is going to have what happening there? Yes, you can read the picture. I want you to think about it. Your position is increasing, 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 and position will not tell us when we reach our highest point. But at our highest point, the rock has to stop before it comes back down. So who is going to tell us when it stops? That would be your velocity function. So we want to know how high, the highest point, that's going to be achieved when your velocity equals 0. Because your velocity is positive as it goes up, but then before it can come back down, which would be a negative velocity, it has to equal 0. So up, positive velocity, 0, and then it can start to come back down. So let's find the velocity function here. How do we do that? Well, velocity, v of t, is equal to the derivative of the position function. Well, they gave us a position function, so we just need to take the derivative. What's the derivative of 160t with respect to t? Well, 160 is a constant, multiple each stays, and the derivative of t is just 1. We talked about the derivative of a linear function being 1, or whatever number's in front. Minus, here we have negative 16, he chills out, multiplies by the power. So 16 times 2, and then t to 1 power less. So we have our velocity. To find out how high the rock goes, we have to set this equal to 0. That's going to give us our time frame. Notice this is not actually telling us how high. It's just the only information we have about height is, well, the highest point is when the velocity is 0. So we're finding out here when it happens. Not how high, but when we achieve the highest point. Divide by your 32. So t equals, divide by 6, so that'll be 5. Let me just double check, make sure I got that right. Calculators, wonderful tools. 160 divided by 32. Yes, I did. So we found at 5 seconds, because that's our unit of time, we reached the highest point of our traveling of our rock. That's the time that it happens. That's when it happens. Now, how do we find the actual height that was achieved? Which function gives us height? The position function. So we go back to s of t, we plug in our time, and that will give us how high we actually reached. So, calculator, make sure I get this right, 160 times 5, 800, minus 16 times 5 squared, 400. So our highest point achieved was at 400, and this is units of feet. That is the highest the rock achieved as it flew above the dynamite. Yes, or as the dynamite made it fly. Part B. What are the velocity and speed of the rock when it is 256 feet above the ground on the way up, on the way down? That's an interesting question. All right, we want to know about this height. But our velocity and speed both depend upon time. All right, remember speed is just velocity with an absolute value sign. So how are we going to find the velocity if we need the time frame for that? Well, this is the height. The height is just another way of describing the position, s of t. If we set our position function equal to 256, we'll be able to find t, the time at which it reaches 256. Once we have the time, then we can plug those into the velocity function to find how fast it's traveling. So we're going to start with the position function because we know the height, 256. We're going to set the position function equal to 256 and solve for t. How do we do that? Well, you have a couple options. I'm going to try and factor it and see what happens. I like my t squared to be positive, so I'm going to bring everything around to the right-hand side. So 16t squared becomes positive. The 160 comes around and becomes negative 160t. And the 256, he's still on the same side, so he stays right there. Now, 16 can go into the first two terms. If it can go into the last term, 256, yes it can, then we can factor out 16 from everything. So if we pull 16 out, we get t squared minus 10t plus 16. Oops. So now we just need to factor that to solve for t. The 16 in front really doesn't do anything because he has no t. We're just interested in the t values. So what numbers multiply to be positive 16 but add to be negative 10? That would be negative 8 and negative 2. So we set each one equal to 0. We end up with t equals 8 seconds and t equals 2 seconds. Wait, what does that mean? Well, think about it. The rock leaves the ground and he shoots up. So on the way up, he's going to reach 256 feet at, well, that'd be the earlier time, 2 seconds. And then it keeps going up and up and up, and eventually it goes as high as it can, and it starts coming back down. When it comes back down, it hits 256 feet again, this time at 8 seconds. So we want to find both of those velocities, because that's what it said. What are the velocity and speed of the rock when it is 256 feet above the ground on the way up and also on the way down? So we're going to plug in 2 for our velocity, and we're going to plug in 8 to our velocity. We found that earlier, so let me circle that right here. We're just going to plug it in. 160 minus 32 times the particular t we just got. 160 minus 64, or 96, and this is velocity. What are the units for velocity? We're doing feet time per second. If you forget, remember velocity is the change in position over the change in time. So you just use the position units divided by the time units, feet per second. V of 8, same thing, just plug in the 8 to your velocity that you already calculated. Make sure I get this right. So 32 times 8. So this is 160 minus 256, or negative 96. Why is it negative? Remember, the first velocity that we achieve, the speed is the speed on the way up. So it has a positive velocity because it's going up. As it starts to come down, the velocity changes to negative because it's traveling down. So on the way down, it has a negative velocity. But look, they actually have the same speed value. So either way, our speed was the same, 96 feet per second. You always just write the positive for your speed. So gravity is really cool. In terms of in terms of an object going up and down, it has the same speed going up as it does coming down at the respective heights. So that's a really cool fact. All right, we answered that one. Part C, what is the acceleration of the rock at any time t during its flight after the blast? So we're not worried about the blast itself. The blast accelerates it, but that's the initial acceleration. What we're worried about is after that, during its flight. So how do we find acceleration? Recall, acceleration is just the derivative of the velocity. Our velocity function was 160 minus 32t. So we write that down, 160 minus 32t. So the acceleration is just going to be the derivative of that. What happens when we take the derivative of the constant? That's gone. So we just have to do the derivative of negative 32t, which is negative 32. Now acceleration has a kind of a funny notation for its units. It's the distance divided by time squared, because this is the change in velocity, and velocity already had seconds in its units. So because velocity already had seconds, and this is the rate of change with respect to time again, we have to put seconds in there twice. So some people say feet per second per second. Another cool thing. So here's our acceleration. So what does this mean? So a negative acceleration means it's accelerating in the negative direction. So if your object is going up, your acceleration is going down, which means your object has to be slowing down. So negative acceleration, when it's opposite of what your object is doing, is slowing you down. However, when the object is coming down, so it reaches its highest point, velocity is 0, now it starts to come down, it's the same direction as your acceleration, so it's speeding up. Okay, so yeah, what acceleration does depends on which direction you're traveling. If you're traveling with acceleration, both of them have the same sign, you're speeding up. If you're traveling against acceleration, your velocity being positive and your acceleration being negative, then you're slowing down. Think of this as gravity, because that's what it is. This is the effect that gravity is having on the rock. Okay, So question D, when does the rock hit the ground again? Okay, well, when the rock hits the ground, what do we know? Well, you can look at this picture and you can read off the graph, but that's not what I want to do. I want to go back up here and talk about this picture. When it hits the ground, what do we know is happening in terms of our position, velocity, or acceleration? Do we know any of them? When it hits the ground, we know what the position is. The position is back to 0. So we're going to take our position function, set that equal to 0. And that will allow us to find out when the rock hits the ground again. So S of t is 160 minus 16t squared. Whoops, 160t. We want to know when this hits the ground, when it's equal to 0. If we solve this equation, we're going to find it. So first of all, factor. I see 16 and t can come out. That leaves us with 10 minus t, all equal to 0. Set each of these factors equal to 0. So t equals 0, and this would be t equals 10. So at 0 seconds, at the beginning, it's at the ground, and then it only takes 10 seconds for this rock to go up as high as it can, all the way back to the ground. Okay, so when does it hit again? T seconds would be 10 seconds. All right, I hope that helps you. I hope that makes sense. If you have any questions, reach out to me, post some comments, email me. Keep studying hard, and I'll see you in the next video.